Welcome to my talk, Building Petabyte-Scale Postgres Clusters. I wish I was there in person, but unfortunately some family emergencies have canceled my travel plans. This is an interesting talk. We will be talking about sort of the challenges that come with moving from a single environment to a distributed environment and all that comes with that. So I'm Chris Travers. I have around 25 years of experience with Postgres, and I've done everything from contribute to Postgres to build distributed systems like we're talking about here. I've worked as an app developer, application developer, software developer, database administrator, engineering manager, you name it. So I've done it all, though perhaps there are many people who are more knowledgeable in a specific area than I am. But I have a lot of experience, and maybe that makes this valuable. So this is a talk about a project that is a re-engineered version of a project that was conceived at a previous place I worked. That was a place called Adjust, GmbH, which does mobile advertisement attribution and analytics. And Bagger was basically our debug log and auditing system for support. Now we're going to talk about why it was built, the general design of their version, shortcomings of the first version. We're going to then talk about what we went about changing and what we went about keeping the same as we built an open source version, and the trade-off lessons. Now, this software is built basically to manage petabytes of logs. It is intended to be something which provides basically extraordinarily scalable management of JSON or any other semi-structured data in variety of contexts. So exciting project, love to get feedback from people, etc. Now, when I was at Adjust, when I joined, we used Elasticsearch. We had about a petabyte of data and 30 days of data retention. The problem was this was high velocity data. So if you take 1 petabyte and you divide it by 30, that would be the same as 100 terabytes divided by 3. That's like 33 terabytes a day. So 33 terabytes a day coming into Elasticsearch. Elasticsearch was extremely unstable, and very oftentimes when you would query it, it would crash. So we moved away from it. When I talked to Elasticsearch people, they're like, yeah, we have people using it up to 1.5 petabytes. Well, we needed something significantly more scalable than that, and we settled on building something on Postgres. At the end, we actually, the joke was that Elasticsearch was a very large, very expensive dev null for us. Dev null being the device in Linux systems where you can write, but you cannot read. Now, specific problems that we had with Elasticsearch was that the protocol for managing different stuff in the cluster is pretty noisy, and when you get a cluster of a certain size, this leads to poor performance. Now, at that scale, then of course you have all the rebalancing stuff that goes on. Elasticsearch is extremely difficult to restart gracefully. You're talking about resetting, one node at a time, hours and hours apart. And if you're trying to do a cold start, it is very, very difficult. Another unrelated problem that we had that I think can be solved with more recent developments since this was that we had garbage collection stop the world events that would last for up to 120 seconds, which is longer than the cluster timeout. So basically, you hit a Java virtual machine, garbage collector, stop the world event, and a node disappears. This causes a lot of rebalancing, which causes more garbage collection problems on other nodes, which can, of course, cause the problem to repeat, and repeat, and repeat, and it can cause a lot of problems. Another problem, which I don't believe has been fixed, is that there was no protection against a Java heap exhaustion. So if you query a very large amount of data, and you exhaust the Java heap, then this causes Elasticsearch to crash. And Elasticsearch client, being very helpful, goes, I didn't get any answer. Let me try running that query again. And so you can basically kill the whole query, whole cluster by repeatedly running these queries. Some of these have gotten better, but I doubt all of them have. I'm sure the garbage collection issues are now solvable. They weren't so solvable in 2018. At the same time, the protocol issues, the difficulty starting and stopping, and the large queries, I don't expect those to have been solved. And finally, the other issue, and this is, I think, a fundamental issue that Elasticsearch has that I doubt has been solved, is that when a new field is found, then there's a lot of cluster coordination to index it, and a lot of heuristics that go into determining what kind of index to place on it. So what this means is, well, this actually causes two problems. The first is that having new fields found in your JSON suddenly becomes much more costly, just simply because it can slow down ingestion suddenly for a while. And secondly, Elasticsearch may in fact choose the wrong data type. Maybe the first instance was fully numeric, and it goes, oh, this is a number, and then later on you see letters, and basically Elasticsearch can no longer handle that. So there are a number of issues that we had operationally at scale with Elasticsearch, and Bagger was designed to solve this. Now, enter Bagger. Bagger is a minimalist design. It basically stores logs on a large number of Postgres systems. It is fully schemaless in the sense that everything is just a JSON document, or in our terminology, a JSON-B document. The idea is that it's linearly write scalable, that you can just add more write nodes anytime you need more write throughput, and the system will just simply adapt. But it's not built for read-heavy workloads. In other words, the general workload is you have a large number of logs coming in. You probably don't want to read all of them, but you may want to read some of them. Which ones you need to read, you're not going to know in advance. So you need to store everything, and you need to read maybe 0.01% of the data, but you don't know which records those are until you actually need them. So write scaling is linear, read scaling is pretty static. Basically, you can query about as much as you can run through the slowest node. So adjust design was this. Basically, programs write to Kafka, Kafka partitioning. Kafka topics are internally partitioned. Those partitions get assigned relatively randomly to consumers within a consumer group. Those each consumer writes to a couple of shards, and so basically a document coming in will end up on a random shard. Then there was a custom tool we called Schaufel, which is German for shovel. And basically, it's a giant multi-threaded data shovel. We would use this to basically read from Kafka right to Postgres. We did patch Postgres a little bit. Actually, I don't think it's probably necessary. You can probably do everything you need to do with compiler flags. So we had bumped up max index keys because we didn't want to index everything on the JSON document. We just wanted to index some things, and basically we ran out of columns necessary. Basically, it just stores JSON-B documents routed by a C language trigger. That C language trigger basically pulls data out from the JSON-B and makes decisions about where to write it. So we used Postgres. Why Postgres? We knew it. But besides the fact that we knew it and we knew it well, we actually evaluated several other projects. And what we found was that Postgres actually had the lowest write amplification of every solution we tested. So when we tested Cassandra, Cassandra had roughly twice the write amplification that Postgres did. And so we chose Postgres largely because, while there is write amplification, it wasn't as high as in other solutions. We really wanted to open source it, but there were a lot of assumptions in that code base that were specific to Adjust's operations, and you don't necessarily want to release a piece of software where you're basically telling the world both how you're running your business, but also basing this software on how you run it, because then it's not going to be as useful for others. And the second was that there was statically defined basically statically defined partition criteria, and basically, again, this meant that it was only really usable by Adjust at that point. So tried to do it. I put time and effort into it. I had other engineers on my teams put time and effort into it, but ultimately we never came up with the time or budget to open source it. Then I left Adjust. 2 years later, I started talking with several other people. These were people who I had worked with at Adjust, and basically they had also left Adjust too. And so at some point we had the crazy idea of, instead of waiting for Adjust to open source all of this. By the way, Adjust did open source Shuffle, but not Bagger. So we were able to take that. But we decided we were going to rebuild something similar. The difficulty, of course, is you can't use any of the original code, which you probably don't want to do anyway. But generalizing it is actually a fairly large challenge, which is why it's actually taken a little bit of time to get where we're at. So several of us came together. We all had experience on the system. We designed something similar. We decided to keep the name. There's effectively no trademark on Adjust's internal project, and unfortunately, of course, Bagger is a relatively weak trademarkable. It's not that trademarkable even in software, right? There are many different software programs called Bagger. So we designed a similar system, and we decided to use whatever existing open source components we had. That included Shuffle, which Adjusted open source, and of course Postgres, Kafka, etc. Our design strategy was go with what we know. And that's because we're dealing with difficult problems, and changes may have unintended consequences. So this is there to minimize unknown unknowns, things that we don't know about. We know, or we don't know that we don't know. So it minimizes the sort of unexpected sharp corners we could run into. And then the idea was that once we have an initial version out, we will evaluate larger changes independently later. Remember, we already had experience with a prototype, or basically the system we had at Adjust. And when I had left Adjust, it had been at 10 petabytes without difficulty. And at that point, it was only storing, I think, 14 days worth of data. So that's... that's like around, I think I did the calculations, is something like, is it 600 terabytes a day coming into the system. At that point, I think our average traffic was around 700,000 requests a second, and we would typically log 2 debug messages from each of those inbound requests. So initial technology choices. Going with what we know, Perl, Moose, PG Object is a framework I wrote some time ago for a different project, but basically it allows us to put a lot of the control logic in a database-centered way. Perl is not in performance-critical paths, but it allows us to move quickly because we know what we're doing, etc., and we have strong Perl knowledge within the team. C language triggers absolutely necessary for performance, And the C language triggers are, in fact, have to be highly optimized performance-wise. Perl Dancer is basically a web services framework for Perl. It's what we use for the query proxy, which I'll mention in a moment. The front end, we haven't really decided on a front end framework yet. That will probably be deferred until after we have a at least usable demo system. And we had decided to add etcd for cluster state management before all of this was going through Postgres listen notify, and frankly, that's expecting every single client to always connect to Postgres directly poses some problems. And then when you add notify to that, there are other concerns that crop up. So we actually made the cluster state handling pieces entirely pluggable. So that doesn't necessarily require etcd. You can write your own that can plug into any basically serializable key value store. So yeah, those were initial technology choices. People will think they're crazy perhaps, but again, they're based on what we had initially. So now I want to talk about the design that we have and how it's different from Adjust's version in the next couple of slides. The thing here is that we have made a few different variations here to what the system we had experience with, but those are designed to be relatively contained, etc. So the first point here is this data flow side, and I want to bring attention here to the service network piece, which is of course where the logs are generated. They get written to Kafka, and then basically you have these shuffle instances, which I sometimes call the shuffle rod, or literally means shovel wheel. Then each shuffle node writes to two different nodes, so we have some redundancy. Because this is a high velocity system, backups are actually really, really, really difficult. And so for this particular system, usually we would rely on redundancy and rather than backups per se. I think one of the problems that we had at Adjust is we calculated that by the time we could restore our backups, the retention period would be over. So there is a problem here with your backups in that particular case. Then on the other side, we have the front end, or perhaps a tool to query whatever. At Adjust, this was just a Perl script that account managers would run from a terminal, believe it or not. But in our version, we expect to have a front end that talks via a REST API to this piece that we call the query proxy. This is basically the web services interface, and it will basically distribute the queries out to all data nodes and then stream the results back to the front end. So just for memory management reasons, we want to stream things back. We don't want to buffer and send. The control and superstructure is more or less similar. You have data center, you have data nodes, you have these metadata servers that we called master servers, but it's a bad description. It basically provides topology of the data clusters, right? And then the shuffle instances connect to the metadata servers to get information about where to connect to. And we actually have a agent running in between that talks to etcd instead of talking to the metadata servers directly. And then we replicate directly from the metadata servers to etcd using logical replication. Then from the front end can talk to the query proxy. The query proxy, of course, will have to get some information from the metadata servers, and then it will primarily ask questions to the data nodes. And then basically, you have a big infrastructure as code repository that manages this whole thing so that you can set up new nodes, drop nodes, rebuild the topology and stuff like that. So current status here The node control infrastructure is complete, reasonably tested, but of course we don't have a full environment up, so it is possible we'll find more issues. The metadata server and schema functions are also complete. We are using Postgres, which is a Haskell system for some web interfaces to wrap a lot of the metadata stuff. Configuration for that is also done. It's easy enough. In fact, that was a really easy piece. The C language trigger, which has been sort of the really big, heavy piece, is now fully in testing. And so now it's just a matter of testing it out and getting the query proxy running, make sure that we can in fact ingest data. And we will be deferring the front end until after GA, or at least until after we have something that's usable for a demo. So feel free to get involved. I will post a link towards the end of this presentation. And if it's possible, from an online perspective, I may try to be available for questions and answers as we get to the end of the presentation. Beyond GA, a couple major things we want to evaluate. The query proxy written in Perl is simple. It's going to be pretty quick to throw together, but there are a bunch of concerns that I think we would all have in terms of running this in a language like Perl. Is there a better language for it? And C sounds, it's nice and high performance, but do you really want to write web services in C? Well, we could do that, but Golang is also a contender, and so is Java. We think the newer versions of Java may in fact have a lot of features that would be really helpful here. So that's one thing that we are in the process of evaluating. Right now, there are a lot of things I don't like about Golang, so my guess is we're leaning towards Java, but the decision really hasn't fully been made. Integration with CitusDB is another possibility. The problem with just simply running this whole thing on CitusDB is that, while you gain a lot of read scalability, you lose a lot of write scalability. But what happens if instead of single data nodes, if you have small Citus clusters? Would that give better read scaling and still allow you to have linear write scaling? That's something we will definitely have to be checking out. I'm also not sure whether CitusDB can properly partition on the sort of criteria that we're looking at. So there might have to be some redesigned pieces in there in order to be able to make use of that if it turns out to be helpful. More generally, there is the question of, can we make this so it can scale reads more? Obviously, if we write more than one place, more than two places, we could spread out the reads a little more. That might help. There might be some other things as well, like, if you write 4 times, then, you have twice the storage, but, you can probably run twice the read queries. Replication instead of write twice. The current system is basically 2 independent writes to 2 independent nodes. This is nice in some regards, but it's also difficult to ensure perfect consistency. So there is the question of, does it make sense to have a single point of truth and then a replica? Don't know about that entirely yet, but these are, again, ideas that we'll have to look at, benchmark, and take a look at. My general suspicion is that replication won't work, just simply because you can write with many threads to write a head log, but you can only replay it with one thread, and that means that your replica might not ever catch up. The one that I'm actually most excited about is this question of impact of compiled block size. So Postgres normally has an 8K block and a target to have at least 4 tuples in each page. However, what this means, if you have a lot of JSON documents, is that a lot of them are likely to go to toast. And if you, and what this means is that reading the document itself suddenly becomes comparatively expensive. So what if we bump the block size up to 32K or even above, basically the maximum supported, and we set the toast tuple target down to, say, 1 or 2. Would this allow us to avoid most records ending up in toast? If so, that might dramatically improve read performance. So that's the one I'm actually most excited about. A couple of trade-off lessons here that I want to talk about. The first one is that scaling, it's real easy to scale on one dimension but not the other. Like if you have a relatively manageable number of writes but you have a massive number of reads, you can just replicate it out, right? Similarly, if you have a massive number of writes but very few reads, like here, you can just ingest it all into different pieces and query everything. The problem is if you're trying to optimize both, then you have a problem. So scaling is easy when you're just scaling reads versus when you're just scaling writes, but when you have to scale both, you do have a lot more that has to be thought about. A second thing is that it's really important to benchmark everything, because what you think might perform well might not perform well. When the initial Adjust version was being built, the initial thought was to have each of the partitioning pieces out of JSON independently pulled out by separate functions. The problem was that the marshalling and unmarshalling the JSON-B just was too expensive. So benchmarking caused a change to how the ingestion trigger was written, and it's something, of course, we've had to learn from also. But again, as we get into everything, we will have to benchmark everything. We will find bottlenecks we hadn't thought about, and we'll have to figure out a way around them. And then the last trademark lesson, which is really important, no, trade-off lesson here, which is really important, is the tension between specialization and generalization, right? So like Citus, for example, is a nice general software, it's a nice general sharding solution. It's going to solve a lot of problems in certain general cases, but it's, you know, if you need something which can do incredible stuff in a narrow case, then you're much better off with a specialized tool which builds that. So you always have this trade-off of, are you solving a general problem or are you solving a specialized problem? We're in the specialized category here. So a few bonus learnings here are, it's really important to know your requirements, right? You have to start from your requirements. If you don't start from your requirements, it's easy to kind of get lost, especially when you're dealing with these sorts of large problems. The second thing is that different architectures apply for different needs. So if you are taking a sort of an approach that we're taking for logs and you try to use it for, say, analytics, you'll probably be disappointed. Similarly, linear scaling, so similarly, if you take a general solution and you try to use it for a specialized solution, you simply won't be able to scale as well, right? So it's important to decide your architecture based on your needs, and that, of course, goes back to knowing your requirements. The last one I want to mention on this slide is the point of scaling dimensions and the challenges that come with that. So linear scaling for reads is easy, linear scaling for writes is easy. Linear scaling on both together is far harder. And the basic reason here is that if you want to optimize for reads, you have a lot more work that has to happen on writes. And so you may have some additional bottlenecks or single points of congestion. I won't call them failure in this case, which may impact your scalability. So that's why I say linear scaling of reads is easy, linear scaling of writes is easy, linear scaling of reads and writes is actually really, really hard. So I'd like to, assuming that I can actually join remotely, I would like to take questions now. Our open source project is listed here at GitHub. It's onemooredata/bagger. And you're also welcome to reach out to me at chris.travers@gmail.com. And if I'm not able to make it to this event live, then I would strongly recommend reaching out to me with any of your questions. I hope to be there next year. And I'm, yeah. Yeah. If I'm able to join at this point, I'd love to take your questions.